Hello student. Today in this session we are continuing machine part 3 session, continuing part 3 session. So we will discuss here one by one. Dear student, in the earlier video we have already discussed about the mechanical advantage, velocity ratio and efficiency also, and we have just find out the relation between the mechanical advantage and velocity ratio and efficiency. Okay, now in this video we are going to discuss about the levers. Okay, it is also important part of any machine. Let's discuss about the levers. Okay, so levers are the simplest kind of machine. Levers are very simplest kind of machine which are used in our daily life. So we can say that a lever is a rigid or a straight or a bent, it may be bent, bar or rod, okay, which is capable of turning about a fixed axis. Means lever is we can say that is a rigid straight bar or rod which is capable of turning about a fixed axis. Means about a fixed axis it just turns. Okay, so the fixed axis about which the lever turns is called fulcrum. Okay, fulcrum is that point about which the lever tends to move, tends to just rotate, or we can say that it turns about a fixed axis. The fixed axis is called as the lever just fulcrum, and the fulcrum doesn't move, it is fixed at one particular point. So this point does not move, means fulcrum doesn't move but remains fixed when the lever is in use. So lever are very simplest machines which are used in our daily life. Okay, which works on the principle of moment. Okay, means turning effect, which depends on the turning effect, and the point at which it turns, that is called as the fulcrum. Fulcrum is always fixed at one particular point, it doesn't move, about which the lever turns. Okay, so this is what the lever, and it has very helpful conditions in our daily life, levers. Okay, so we are going to discuss about the principle of lever. Okay, that what are the various principle of lever, what are the mechanical advantage of lever or a velocity ratio, and how it is helpful in our daily life. Okay, so here are three kinds of lever. The first one is called as the first class lever, this is second class lever, and this is third class lever. In this first class lever, the fulcrum is in between the effort and the load. Okay, and we can say that here the fulcrum is denoted as point F, and about which it is fixed, and about that the effort turn about the fulcrum, and the load is also turns about the fulcrum. In this particular condition we are able to use it. Okay, so the straight line AB, okay, is a kind of lever. AB is a lever in which the fulcrum is placed at the middle. It may be middle, or it may be it is not necessary that it will be exactly at the midpoint, it doesn't mean. So here is a fulcrum, and effort E is applied. Effort E is applied at point A of the lever, just overcomes a load L, here is a L at point B. Okay, from the fulcrum F, the distance FA, this is the distance FA to a point B. Okay, or we can say that the distance FA is called as the effort arm. Okay, and the distance FB is called as the load arm, at which the load is just acts on point B. So FA is called as the just effort arm from point A, the effort we are applying here. So FA is effort arm, and FB is the load arm, at which the B at position B the load acts. So these are the just arms. Okay, and on the basis of these arms we can able to just say that which machine, which kind of lever is used as a force multiplier, or which is helpful in gain in speed. Okay, depending upon the relative position of the effort and the load respectively. So a lever, any kind of lever, whether it is in a first class or second class or third class, it always works on the principle of moments. Okay, moments means a turning effect. We have just read in the earlier chapter also that it is works on the just moment of force. Okay, so in order to make it equilibrium position, okay, we always say that moment of load about the fulcrum, must be equal to the moment of effort about the just fulcrum. Okay, so these are the conditions in order to make it in equilibrium. So, and all these moments must be in the opposite direction. Suppose it will be in the clockwise direction, obviously it will be in anti-clockwise direction. So the direction should be different, must be different, and it will be in equilibrium condition. Okay, all the turning effect is always towards the fulcrum. So we can write that how we can write that here you see say it that clockwise moment of load, clockwise moment of load about fulcrum just equal to anti clockwise moment of effort, anti-clockwise moment of effort about fulcrum. Means what we have here, just we are getting here that all the clockwise moment of load about fulcrum is equal to anti-clockwise moment of effort about fulcrum. Means here load is in what, if you are turning in this direction, then it will be in a clockwise direction, and effort, if you are turning about this in the fulcrum, so it will be in anti-clockwise direction. And in order to find it in equilibrium condition, it is just principle is here that it always works on this principle, that is a clockwise moment of load about the fulcrum equal to anti-clockwise moment of just effort about fulcrum. So this both the just condition should is necessary. Okay, it is required. So what we can write, load about fulcrum, we can write that whatever the load is there, that is load into FB. Okay, load into FB, we can write here load into FB will be equal to just effort into FA, and after that if we just rearrange it, that is load upon E will be equal to what, FA into FB. And what is FA? FA is effort arm. This is effort arm. And what is FB? FB is a load arm. So, and what is the ratio between the load and the effort? What is this? Load by effort is what? It is mechanical advantage. So we have got one relation here, effort arm upon load arm. Okay, so mechanical advantage is equal to effort arm upon load arm. So in case of levers, how we can able to determine the mechanical advantage? Mechanical advantage is equal to the ratio of effort arm to the load arm. Okay, and due to relative position of the load arm and the effort arm, we can able to differentiate class 1, class 2 and class 3 levers. Okay, so this is what the condition. Okay, we have to follow it. So here is the condition we are getting here, MA equal to effort arm upon load arm. So dear student, So this is the relation, okay, this is the relation, and this is what we called as the just so this mechanical advantage is equal to the length of the effort arm to the length of the load arm. This is a ratio, and this is what we called as the relation. This relation is known as the law of lever, okay. This relation is also called as the law of lever. This is the law of lever. So the mechanical advantage of a lever is equal to the ratio of the length of its effort arm to the just length of its effort arm, okay, effort arm to the length of the load arm, okay. This is what the mechanical advantage, and this is what we called as the law of lever also. And from this condition, okay, we have just concluded one thing, that if one condition is there, that is if effort arm is equal to load arm, it means what? Its mechanical advantage is always equal to 1. This thing you have to know, this is you have to just identify. And what happens when effort arm is greater than the load arm? Mechanical advantage is always greater than 1. And what happen when effort arm is less than the load arm? Mechanical advantage is always less than 1. So these are the criterias, and on the basis of this we can able to determine the machines. So, and dear student, we know that is the we are talking about the ideal machine, okay. We are talking about the ideal condition of lever, okay. And in this we know that in an ideal machine always mechanical advantage in the velocity ratio is equal. So if the effort arm is greater than the load arm and the mechanical advantage is greater than 1, obviously velocity ratio will also be greater than 1, because we are talking about the ideal condition, okay, here. So all these three conditions we will discuss one by one, okay. And depending upon the condition of the relative position of the effort for load and fulcrum, the three kinds of levers are just differentiated. If the fulcrum is in between the effort and the load, and the effort and load are in the same direction, then we can see that in the downward, so we can say that this is the condition of first class lever. And what happens when the just load is in between the fulcrum and effort? Load is in just clear it, load is in between the fulcrum and effort, and the direction of the just load and the effort is in opposite direction, okay. This kind of lever is what we can say second class, okay. And what happens when the effort will just in between the fulcrum and the just load? We know that the fulcrum is fixed position. This is fixed position about which the lever is just tends to move or rotate or a turn, okay. So in this condition effort is in the upward and load is in the downward. So in this case also the effort is in between the middle, and the direction of the effort and load is in the opposite direction. So this kind of lever is called as the third class lever, okay. And we know that all these are the criteria of any just lever, okay, how it works. So if you talk about the first class lever, that is the first condition, when the fulcrum is in between the effort and load, what happens that it doesn't necessary that the fulcrum is in between the middle, okay. It may be, it is not necessary that fulcrum is on exactly at the midpoint. It may be somewhere in the between the effort and the load, okay. So these are the condition. And one thing that you have to keep in your mind, that for first class lever, that is for if you talk about the first class lever, just see here, for first class lever, just mechanical advantage and velocity ratio, we are talking about the first class lever. For first class lever, mechanical advantage and velocity ratio, okay, just can have any value. It may be either greater than 1, okay. It may be just mechanical advantage, or equal to velocity ratio is equals to 1, it may be mechanical advantage, or velocity ratio less than 1, it may be at any condition the first class lever satisfies this. Okay, so what happens, that is, if you talk about this one, when effort arm is greater than 1, so if the mechanical advantage will be greater than 1, then velocity ratio will be also greater than 1. Why? Because we are talking about the ideal machine, and in ideal machine mechanical advantage and velocity ratio of any ideal machine is always just equal, so we can taking the consideration here. So mechanical advantage is equal to velocity ratio, means mechanical advantage and velocity ratio is greater than 1. In this case, dear student, the first class lever acts as a force multiplier. Okay, we have discussed the force multiplier, that with less effort we can able to just find out lift a heavy load. Okay, it acts as a force multiplier. So in this case, mechanical advantage and velocity ratio should be greater than 1. We can take the example of crowbar. Okay, we can also take just a spoon which is used to open a lid of any container also. Okay, claw hammer also. Okay, so these are the examples. Okay, the first class lever. So first class lever mechanical advantage velocity ratio always greater than 1. That is why it acts as a force multiplier. That is force, it acts as a force multiplier. This is acts as a force multiplier. And what will happen when mechanical advantage and velocity ratio is equal to 1 in case of first class lever? In this case, it will just if mechanical advantage and velocity ratio will be equal to 1, in this case the just exactly equal. Okay, that is effort arm and the load arm is exactly equal. It means that effort arm and the load arm is exactly equal. We can take the example of physical balance. Okay, fulcrum is in between the middle and the just exactly they are balancing. Okay, so in that case we can take the example, that is effort arm is equal to load arm. In that case, in this case what happened, we can take the example of physical balance, and what happens when mechanical advantage is just equal and velocity ratio is less than 1. In this case also we can say that effort arm is less than the it means that the effort arm is less than the load arm. Okay, effort arm is less than load arm. In this condition we can take that it acts as a gain in speed. If this condition holds, then it means that effort arm is less than load arm and it acts as a gain in speed. We can take the example of scissor. Okay, that with the displacement, with a large displacement of load, this is occurring with a small displacement of the effort. So in this case we always just gaining the speed there. So these are the example. We can also take the example of scissors also. Okay, so this is all about the first class lever. One thing, just I am reminding once again, that when the mechanical advantage and velocity ratio is greater than 1, that is in this case we can say that when the effort arm, in the meaning of this is effort arm is greater than the load arm. In this case it acts as a force multiplier. When the effort arm, that is mechanical advantage and velocity ratio, is equal to 1, that is if the effort arm is equal to load arm, in that case we can take the example of physical balance also. Okay, it will be equal to 1. Okay, and in the third one, if the mechanical advantage and velocity ratio is less than 1, that is it acts as a gain in speed. It means that effort arm is less than load arm. Okay, in that case only it is helps acts as a gain in speed. We have taken the example also. So these are the examples, okay, of the first class lever. It is just acting along the 3 conditions. Okay, different 3 conditions. And what about the second class lever? In second class lever, here we are just considering here the load is in between the just fulcrum and effort. In this condition what happened, that effort arm, second class lever, in second class lever, effort arm effort arm is greater than the load arm. This is the criteria. Effort arm is also greater than the effort, because here you see there fulcrum is here, the total distance of the effort is greater than that of the load. Okay, so effort arm is greater than the load arm. In this condition, always mechanical advantage and velocity ratio is also greater than 1. Okay, if the effort arm is greater than load arm, the mechanical advantage and velocity ratio is always greater than 1. This I have discussed in this first class lever also. So with taking the concern this, what happens when mechanical advantage and velocity ratio is greater than 1, and what happens when effort arm is greater than 1? It always acts as a force multiplier. Okay, it acts as a force multiplier. So whenever the second class lever is always acts as a force multiplier. Okay, we can take the example of nutcracker. We can take the example of nutcracker, and we can also take the example of a bottle opener. Okay, that is, its handle is so long, okay, and with that only it is able to lift a heavy load with applying less effort. So these are the just second class. Okay, now we will talk about the third class lever. In this lever, effort is in between the fulcrum and load. What happened in this condition? You see the load arm is greater than the effort arm. This is effort arm, this is total load arm. So in this case, in third class lever, what happened, that load arm, or we can say that the effort arm is less than the load arm. In this condition, mechanical advantage and velocity ratio is also less than 1. Okay, so the third class lever always acts as a gain in speed. Okay, just gain in speed. We can take the example of scissors. Gain in speed, that is, it simply means that the displacement of load is just larger than the displacement of the effort. Okay, it only this much you know. So we can take the example of scissors also. Okay, so if you talk about the just first class lever can act is all the three. That is, it acts as a force multiplier, it acts as a gain in speed, or it may be equal. Okay, example I have taken physical balance. Second class lever always acts as a just force multiplier. Why? Because the effort arm is greater than the load arm. Okay, always acts as a force multiplier. And in third case, that is third class lever, load arm is always greater than the effort arm, that is effort arm is less than load arm. In this case, it always acts as a gain in speed. Okay, and mechanical advantage and velocity ratio is less than 1. Okay, in the third class lever. Second class lever, mechanical advantage and velocity ratio is always greater than 1. Okay, and it possesses all the three conditions. It may be greater than 1, it may be equal to 1, or it may be less than 1. So dear student, this is all about the levers. Okay, just go through. We will meet in the next video. Thank you.